So recording has started. I'll be, yes, please. Okay, fine. So in this session, I'll be showing how to design a patch antenna, right? So this is going to be the patch antenna, and a coaxial feed is also present. So this is a simple design. A slightly complicated design is provided over here in this set of slides, which I'll be sharing after the presentation, right? So I'll be sharing it in the Teams. So again, step-by-step procedure for this one is also given. So let me go ahead and start show the design, how it is going. So why do we need to design this antenna and so on, I mean, patch antenna and so on? I'll just briefly this. So Microstrip Patch Antenna, we will be required to use antenna at frequencies beyond 1 gigahertz, not less than that. So you can fabricate multiple antennas like this in the form of an array, and you can get improved radiation characteristics. So the advantages include low profile, easy to fabricate, easy to feed. That means coaxial line or microstrip line. Easy to form array, and moderate directivity will also be there. Disadvantages are its bandwidth is slightly less, and bandwidth increases proportional to the substrate thickness. So how we select the substrate, the dielectric thickness, and so on. Relatively, they are low efficient as well. So how the design is going to look like this. See, there will be a ground plane below, which is the orange color sheet, a very large sheet. Then above which there is a gray color block, right? So that is a dielectric material. So a dielectric material, let's say it is FR4. FR4 is one standard dielectric material of multiple thicknesses. It comes with it, but the height H we will be preferring 0.8 mm. And the top rectangular sheet is there, right? So that is the this particular sheet is basically the patch antenna, microstrip patch antenna, the rectangular top one. So we have a metal below it, then a dielectric and a metal. So the cross section is going to look something like this. And see, the green color line is there, right? That is an coaxial probe. So the ones which are below, right? That is a coaxial conductor. So again, what it is, I'll show it in the next, this one. So you are going to give the feed input at a particular point offset from the center, so that you are actually generating the radiation pattern around it. So the standard formulae are given over here. The length, the frequency, how it is dependent, how the effective dielectric constant changes, and so on. So all of these are given over here. But if you want, you can look at this particular this particular link, wherein we can calculate the microstrip patch antenna if we give the dielectric constant, the dielectric height, and the frequency at which we want to design. Right. So in this PPT, I'll be sharing it. So we have made a design of up to around 6 gigahertz. Right. We'll be having this microstrip patch antenna fed through a microstrip feed line, inside feed line. So instead of having a microstrip feed line, I thought I'll share this document with you for your reference, but I'll present a video. I mean, in the video in the demonstration, I'm going to create an antenna array, right? A single antenna will perform like this, right? We'll design this antenna. Then how to have an array of antennas. Array meaning like this, some 2x4 antenna array. You can see, select it. See, there are 8 2x4 antennas, and the circular ones are basically the feeds are below. So if you are arranging multiple antennas like this, how the radiation pattern is going to change. So those you can do, and I've already done some radiation pattern. I mean, today only I just made a design. especially for 20 gigahertz, because I have worked on lower frequencies, but the 5G and 6G and beyond, everything it's going to be close to 27 or 28 gigahertz. So it is a need of ours that we look at that frequencies as well. So that's why I've just made this design for 27 gigahertz, especially, right? So the overall antenna size, if you look at, right? So 4 antennas, the width is around 2 centimeters only, 20 mm or 2 centimeters. You will get 8 antennas within that, and then the height will be like 1 centimeter. 2 cross 1, 2 centimeters cross 1 centimeter. Within that itself, you will get 8 antennas, and you can get unique radiation characteristics. That means very good gain also you can get with it. So 20 times the power it will pump in one particular direction like this. Also, you can what you can do is you can change the phase shift, and the beam will rotate basically. What I'm telling is, so let's say the structure is same, right? I'm not modifying the structure. Only one parameter I'm going to change, which is this 5 value. You can see, right? This value, let me change it to 30 degrees. Right? I'm just changing it to 30. So it just a minute. So the beam, if you can notice, it has tilted slightly to the right. So if I'm changing it as 45 degrees, then the beam would shift again to the right. So if I'm changing it to minus 15 degrees, the beam is shifting the other direction. And minus 30 degrees, the beam is shifting again towards the left. So basically what we are getting is that when you are scanning, right, you are scanning along the structure, so you are radiating at individual directions. So these kind of applications, I mean, it includes 6G or 5G communications, and I mean, multiple other vehicular applications as well, and in your mobile phones, multiple antennas, not a single antenna, but multiple antennas will be there. So how to model it? That also showed in today's presentation, right? So let me just take these parameters, right? I'll be using the same set of parameters in the new design. I'll just show it to you, right? And just let me make a note of the same, right? Values and the variables which I. So where I'm using what, I'll tell you what it is, right? So let's start a new design. So this one I'm just keeping it aside, and I'll just minimize this window, and I'll start a new window. So for any of you who wants to design an antenna at any different frequency, right? Any other frequency, you can look at this website, right? EM Talk. You can just Google and see Microstrip Patch Antenna Online Calculator like that, and you will get this website. And in that you can enter the values, but this gives an approximate value. This is not the accurate one. Again, you might need to fine tune it. So even this design, whatever I'm going to show it, right? It is a fine-tuned version of it. It's not the one which the website said, but you can take that as a starting point and proceed. So as usual, you're going to select this HFSS design. Once you open a project, you're going to select this HFSS design, so that HFSS design is going to be uploaded or included inside the project. So once it is included, first thing, as I told you earlier, you'll have to save it. Right, so keep saving the content, because there are chances that system can crash, or if you are increasing the number of simulations, then it might. Let me put it at 27 gigahertz and done during session. So I'm just naming this design as single antenna, single element design. Right. So one element we are going to include, I mean, present out here. So first thing, we are going to utilize the coordinate system. Right. So with respect to this one, 27 gigahertz, the half wavelength corresponds to 5.55 mm. Now, this 5.55 mm, I'm going to use it for the ground plane and dielectric. So, let me just quickly draw out here. So, you're going to draw a ground plane like this, right? So, this one I'll mark it as 5.5 mm. There is a reason why I'm just again taking it as lambda naught by 2. That is for array configuration, right? This also we'll be taking it as lambda naught by 2, which is 5.5 mm. Now, we'll mark the center of this as the origin. We'll keep this as the origin. Then we'll draw a ground plane of a small thickness, right? That thickness is 0.05 mm. 0.05 millimeter, right? So 5.5 mm, we are going to name it as WG, ground's width, and this is also going to be WG. So if this is origin 0, 0, central point, right? The corner point will be at minus WG by 2, comma along X, along Y minus WG by 2, comma 0. So this will be the starting point, this corner point that we are looking at. Then from the starting point, along X, you're going to extend the block up to WG. Along Y, you will extend up to WG, right? This is X-axis, this is the Y-axis, right? Let's say like this, right? So the axis should be on the other side, but anyway. So Z-axis will be along the vertical point, right? I mean vertical direction. So the corner, we are selecting one corner point. Let's just a minute. So this corner point is being selected, right? As minus WG by 2, minus WG by 2 and 0. And from there, along Y direction and along X direction, you're going to move a distance of WG. And height, it is going to be the H value, which is 0.05. So let's construct this ground plane first. So go to this block or go to draw and box and click on 3 places on the screen. Now, first step, what you need to do is just double click it or right click properties. See on create box, you can select it. So type the minus WG by 2, comma minus WG by 2, comma 0. Now, when you click outside, it is going to ask what is the width. So I'm going to take it as the 27 gigahertz wavelength. Right? It's half of the wavelength, which corresponds to 27 gigahertz, which is 5.55 mm. 5.55 mm. Click OK. Okay, just a minute. I think I'll have to change the resolution so that it will be a bit more visible. It's becoming smaller. Yeah, I'll have this resolution, right? I believe now you will be able to see it clearly. Minus WG by 2, minus WG by 2, and 0. Right. So the width is going to be WG, and the length is also going to be equal to WG. Height, it's going to be T. Thickness, it's going to be 0.05 mm. Okay. So basically we have drawn this ground plane. Again, just to cross check 0.05, 5.5 mm and so on. Okay. So click OK. Now, once the ground plane is ready, we are going to construct the dielectric box. So click another 3 points. Now go into the paint, right? So now you're going to start from this corner point. So please note from the origin, from the initial point, the x and y coordinate remains the same as this minus wg by 2 minus wg by 2. Right? And thickness is t. Right? So the topmost point, so that is minus wg by 2 and minus wg by 2 and t. So we'll go ahead and model the same like this, right? So it is minus wg by 2, comma minus wg by 2, comma t, the thickness which we had given previously. So wg and wg along y, and along height we are having a h which is 0.8 mm. 0.8 mm is one of the standard FR for the materials which are available in the market. Now, having said this, what we are going to do right now is we are going to draw the patch antenna. Now, patch antenna, it is going to have an x and a y direction, right? So what we'll do is we'll draw a width and a length, basically, right? So I have just written this. Okay, 1 minute. The notepad is there, right? I'll zoom out, right? So the width of the patch antenna is 3.3 mm and the length of the patch antenna is 2.25. And this patch is above the dielectric and the ground plane, right? So you just mark these values, something like this. So the third box which we have drawn is minus w by 2, right? Width half of the width, comma minus l by 2. It is t plus h. The width of the patch antenna is 3.13. Length of the patch antenna is going to be equal to 2.25 mm. Which, right, the starting value I have written. The width is W and L along y direction, and height is the thickness, metal thickness as before. So we would be getting this structure. Now let me name it. See this box 3, you can go over here and select patch antenna. And the material, there itself you can edit it. So we are going to select the copper conductor. So the patch is designed as a copper. Then the ground plane should also be a copper. So let me name this first. We can change the color as well. So just a minute. The ground plane also, I'm just naming it like this. Then this dielectric material is going to be, so right click, assign material. Select FR4 and click OK. So we have right now drawn a patch antenna. Now the important thing is we'll look at this structure. See, along the length of the antenna, right, we are having an offset, a particular offset, and that's where our feed line is going to be. Inner conductor will be there. Then outer conductor and dielectric will be restricted over here, right? So we are going to feed the signal over here. So we need to identify roughly how much is it, I mean, how far is it from the central point. So now, so we are going to just offset that feed. So I'm going to use it as I'm going to offset the coaxial probe itself, probe location. First, we'll offset the coordinate system. See, what we are doing is this coordinate system, default coordinate system is there, right? That one I'm going to offset it. So offset, I'm just going to click at random place. Then over here, I'm just naming it as a feed start. We're going to start the feed along this path, right? So this feed start, you double click at it, it is going to provide you the starting point where you should. So see, the feed point should be along the y-axis. Along the y-axis, it should be offset from the center, not along the x-axis, because x-axis is the width. Our feeding should be done along the y-axis. So this feed start, the feed point will be somewhere out here. So x is offset is 0, y offset. So the origin point, we are just offsetting by let me just name it as L underscore offset times minus L by 2. Right? So L offset is a parameter that we'll be using it. Again, we'll see those in the later stage. And the feed line, I want it to be below the ground, or the value is going to be, let me take it as Z underscore feed. So what is L offset? L offset is just 0.77. Right? So then it is asking Z feed. So I just gave it as 1 mm. Right. So 1 minute. Has come a bit farther away. Wait just a minute. So the global coordinate system is exactly along the center, but we are offsetting along this direction. So the feed start, it should be somewhere out here. L underscore offset times minus L by 2. So the feed start has been just offset. We are going to take a reference point like this, such that we'll be able to perform the, see, this feed start is there, right? Why we are offsetting is the side impedance will be close to 200 impedance, 200 ohms. The central impedance will be close to 0 ohms. Now we need to match our feed line, which is 50 ohms, to this structure. So that has been optimized, and I have taken that particular value like this: L offset times minus L by 2. Now we are going to feed at this point. Again, please note, along the z-axis also we have to include the length. So I'm just putting this as the feed start value as minus z feed. So we're going to give feed from here, from the base, and outer conductor will be until this metal, and dielectric will also be, along the ground plane, right? And only the inner conductor will tend to go to the top. So we have to draw 3 cylinders. So first cylinder is right. So we'll be using one of these at the feed point. Now let me select this and enter the feed value. So I'm just writing it as inner conductors. The cylinder, when you double click at it, it's asking the start value. So it is just 0, 0, 0, and the axis is along Z. The radius is 0.2 mm. Note these dimensions are specific for only this 27 gigahertz antenna. So height, it is going to be Z underscore feed plus H E plus H, right? So the inner conductor should go until the top plane. So you can just write like this: Z underscore feed plus the thickness, ground plane thickness, the dielectric, and the patch antenna. So for this, we have given like this, and click OK. So you will get this inner conductor extended up to here. Now, this is a metal. So I am just going to so see, once this inner conductor is there, then we need to have a dielectric medium. So before that, I'm just assigning P to this material inner conductor. Now next we are going to draw the dielectric, the Teflon, which is around the coaxial probe, and then we will be drawing one more metal around it. So let me just draw this draw box. So the center point is going to remain the same. So this one, we're going to take it as point yeah. So the radius, it is going to be 0.7 mm, the dielectric. So the height of the cylinder is going to go from Z underscore feed as thickness. So if you look out here, right, there is an outer conductor. So there is a inner conductor. Now there is a cylinder. This cylinder we have not configured anything as of now. So one more dielectric should be there. Basically, the Teflon should be there between the inner conductor and the outer conductor. So if you click right, so see, this inner conductor should come and touch the top of the antenna. That is the main design, right? So what we have designed right now additionally is this inner connector. This is the outer conductor, and this should be the dielectric, let's say. So FR4. Right. So we'll select the radius as R underscore dielectric. So the height is this much, and the material properties we need to change. I'm just putting it as a PEC material, perfect electric conductor. Now the dielectric is also placed, then the inner conductor should also be mapped. Just a minute. Inner conductor is there, and then we should have an outer conductor. See this this surface, we have selected it for the dielectric material, and then this one should be 0.8 mm and a height of Z feet plus T plus H plus T. The thickness basically. So click OK, and this is the outer conductor. In fact, outer conductor need not come until the top two, so they can Um, so now the structure is completely formed. Basically, I'll just quickly show. See, this is an dielectric material. So over here we have the inner conductor. I'm just naming it as inner conductor, and the color I'm just selecting it as then. So first one we have just marked it as the inner conductor. Then this one is the dielectric material or the Teflon. So go to assign and type Teflon. So it will get selected. So click OK. And then we have the outer conductor, right? So outer conductor, this portion needs to be subtracted, right? So see, over here we have taken it as this PEC as the outer conductor. And then we have the Teflon. So name itself, I'll just so all we need to do right now is subtract a copy of all between this dielectric and the ground plane, right? So how to do that is, so there are two things that you need to consider. One is the Teflon and one is the inner conductor. So both of these you just go to edit and duplicate around axis. Basically we are just I'm going to put it as a 360 degrees. So inner conductor 1 is created, right? This inner conductor should go through the dielectric and go through the this base metal, right? So this one should be subtracted. The copy of the inner conductor should be subtracted from the Teflon also, right? And additionally, the Teflon's copy. I'm just creating a copy. Edit, duplicate. Right. So when you give around the axis, you will get something like this, right? So this one will be subtracted from outer conductor. So once we merge the outer conductor and the ground plane, so you can click like this, the ground plane and this one. So Boolean unite. So edit Boolean unite. So if you click, so the outer conductor means it also includes the, I mean, I think I subtracted the wrong one. So the ground plane and outer conductor and this copy of the Teflon. So right click, edit, Boolean subtract. So from the ground plane, we need to remove these. So when you click like this, the ground plane minus this one will be the remaining one. So when you click OK, you'll be able to see that along the ground plane, you're able to see the slot. Now, simultaneously, right, inner conductor. See, the Teflon is placed over here. The ground plane, outer conductor, I think the outer conductor. So I'll just undo it. So this outer conductor is there, right? So this ground plane and outer conductor, what we can do is we can just even merge it. So edit, Boolean, unite. So once it is uh, united, so what you can do is from this we need to separate the Teflon's region. So along the outer conductor, we need to subtract the Teflon's copy. So go to edit, Boolean, subtract. So from the outer conductor, Teflon will be subtracted. So we are having a clean outer conductor like this. A copy of Teflon was initially created. Now that copy also should be subtracted from right. So this one passes through the Teflon. So we need to cut that also. So you can just create a copy of the inner conductor, which is this one. And see the Teflon's region, it should be subtracted from this one. So Teflon and copy of the inter. So from the Teflon, when we are creating a copy of the inner conductor and performing like this, so you are getting this complete structure, right? So the ground plane is in fact connected to the outer conductor like this, and this is the dielectric material, and this is the antenna, right? So we are feeding this antenna. Now let me just save this. Now there are certain things that you need to perform in addition, right? So let's look at this. The first step, you need to create a boundary, right? So right click, create open region. You can give the frequency as the design frequency, which is 27 gigahertz, and click OK. So by default, it is just created. A big space around this. So I'm just saving it then and there. So an airbox kind of region is created, which is going to have a boundary, right? So now you have all the structures ready. So this is the Teflon, this is the outer conductor and the ground plane. But the outer conductor and the ground plane, there is a slot as well. The inner conductor is coming. And you have this structure, the whole structure as shown out here. Now, once this is done, what we need to do is we need to create a port also. The port, how to create is so just a minute. Right. So what we need to do is we need to provide the excitation. So go over here beneath it and select F or face. So in this object one to face, right? And select. Okay, I think the outer box is not letting me this long, right? Out here, you need to select the faces, click F, Okay, the airbox is creating trouble, so let me just hide that airbox. So the inner conductor and the outer conductor, right? They are, I mean, we are going to feed via the ground, right? Below the ground, we are going to feed it. So we need to select this face, we need to select this. Then once you select all three faces, now we can draw the port, right click. So it is asking the integration pattern. So you need to move the mouse pointer to the center so that there will be a circle. And then along the x-axis, if you notice, it is creating a box. So when you click over here, it will show it as defined. If any mistake is there, it will show undefined. Right? Now, click next, and yeah, this gives us the excitation, electromagnetic excitation from the beneath towards the antenna, and the antenna is in turn surrounded. So once this block is done, right, all you need to do is take the setup, go to add and create this advanced setup. So what we'll do is we'll initially plot I'm giving multiple subsequent frequencies. The lower frequency you can give it as 24 gigahertz, and high frequency you can give it as 30 gigahertz. Maximum number of buses 6 and so on. Now click enter. It is going to ask how many points do you want to simulate. I'm just going to reduce it to a bit less. So this actually sets up the starting frequency, stopping frequency, and how many number of points we are selecting, and so on. Now click this save fields at basis frequencies and save radiated fields only, and click OK. Now we have almost completed all the steps, right? So usually the feed point is there, right? So that will be slightly offset, right? So along the center, from the center towards the edge of the half, right? The total length is like this. Then from the half, you have to take somewhere close to at least 50% of the remaining portion from the center to the edge in that region. However, if it is appropriate, you can fine tune it in such a way that the field distribution is the field distribution will be properly obtained, right? So just after this, once one antenna is ready, so the radiation surface also I'll just put it over here. Yeah. Now this is a radiation surface. It is going to radiate the power outwards. So again, save it once. Now analysis also is set up. Next is go to the validation check, HFSS validation check. So it says that there is some error with respect to 3D box. So the patch and inner conductor and box and inner conductor are intersecting. So again, this is a critical issue. So let's look at it. Now go to tools and design settings. In that you can enable the material override. What it does is it is going to override when two materials overlap. Which one to precipite? It is going to be based on the electrical conductivity. It will, I mean, whichever one is the best possible way. Okay, there is some error, I guess. Just a minute. Let me change the patch also to PEC. Right. So there is an overlap that has been avoided. So let me check this. Box 2 and inner conductor. So the box 2 is this dielectric material, and we have an inner conductor also. Inner conductor is this vertical element. Now there is a metal and a dielectric. So ideally speaking, the metal should take. I mean, when overlap occurs, one of them, the metal one, will have its preference. So now, if we go and right. So this one again, I'm just going to create a copy. I'm creating a copy and pasting it here. Now this one is separated from this region. So go to edit. Boolean subtract. Sorry, just edit Boolean subtract. Now the inner conductor's copy should be over here, and the box should be like this. Now when you click OK, the FR4 will also have a slot like this. Now, having said this, if you just check the validation, perform validation check, it will be all green, meaning you have drawn successfully this antenna. Now, all you need to do is just go over here in the analysis, right click, analyze all. If you click it, it will start simulating the antennas. So there is this error that's happening. Waveport to solution domain not fully backed with PEC. Right. So one more thing I just wanted to inform you that if you are drawing a waveport, then it should be backed with a PEC. Meaning this face is there, right? At this where you are going to give the waveport. So instead, if you give lump port, it would work fine. If you are giving a waveport, it is always advisable that it should be backed with a conductor. So what you are doing is you're just drawing a PEC. Go to edit, assign material, and draw PEC, perfect electric conductor. So click OK. And in this one, so origin is the starting point, and R underscore outer or 0.8 mm we can give, and the height is, let's say, 0.2 mm. So when you click OK, it is going to be expanding. The height should be negative. I'll just show it once I just select it. So once, see, if this is a wave port, it should be supported by a metal. So this block, it is going to be a metal. So that block is going to be shielding that wave port. So wave port means you should select that. I mean, it should be backed with a metal. Now go to analyze all, and now the simulation would start. So what sweep that we have kept is 24 gigahertz to 30 gigahertz at 20 points. It is going to calculate. Right. So this is the setup that we have done. Now, as the simulation is going on, what we can do is see adaptive pass 4, adaptive pass 5. It is fine tuning each and every analysis output. So what output that we are going to plot are go to result, right click, create model solution data, and you can select the 3D plot. So just a minute, I think the completion is done. So right click, create model solution rectangular plot S11 dB. You can just select this S11 and click new report. So in the new report, once it is generated, you are able to see that you're having a dip of at 26 gigahertz. You had intended for 27 gigahertz, but the dip has happened at 26 gigahertz. But 27 gigahertz is also well below minus 10 dB. That means there is a very good chance that you are going to get a good radiation pattern below it. So minus 10 dB is where we look for the bandwidth. So you right click marker and add marker. You mark this point and let's say this point. So you're going to get a bandwidth close to 4 gigahertz, right? Minus 10 dB bandwidth. That means you give some power into the port, into the antenna, it is going to come back. Only 10% is going to be reflected back. Maximum 90% of the signal is going to be coupled to the antenna. So let's add a marker at 26 gigahertz also. So close to 26 gigahertz and 27 gigahertz also. So at 27 gigahertz, we are having close to minus 16 dB, and 26 gigahertz, we have close to minus 29 dB. That's the S parameters. So scattering parameters, what it says is, I'll repeat it. Whatever signal that you're going to give from here, that signal is effectively coupled to the antenna. Right? It need not necessarily mean that the antenna is having very good radiation characteristics. All we are telling is impedance is perfectly matched, so no reflection. Respect to S parameter. Now, to look if the antenna is actually radiating, so you need to right click over here and create far field report and select the 3D polar plot. Now, gain in total, right? So go to the families, and here we had selected only 27 gigahertz for radiation. So I'm just selecting it. So here you are able to see the radiation characteristics of a microstrip patch antenna that has been fed with the coaxial probe at 27 gigahertz. Right. So this is the 27 gigahertz antenna, I mean the corresponding antennas radiation pattern that you're able to get. Now, again, just as discussed in the afternoon, if you want, right click antenna far field report. If you want, you can plot it in the dB scale also. So go over here and select the dB scale, gain, and in dB, select new report. So this is the decibel scale. So dB scale, the value comes close to 5.8 dB. So as I told you in the PPT, right? Why do we use this? It has moderate directivity, close to 6 to 8 dB gain, right? So close to 8 dB gain, you will be able to get along a particular direction. Now, what to do to get an analysis about if you are going to perform an array analysis, right? Like if you are going to plot multiple antennas. So one antenna we have designed over here. This antenna itself you can fine tune further using optometrics. So you can go over here and add parameter, add a particular parameter. Let's say the feed point or whatever it is, L underscore offset, which is 0.77. If you want to modify it as 0.8 or something like this. So, or any other parameter if you want, you can alter it so that you can get a new design for a respective frequency which you intend to design for. Now, for the array concept, right here, only one antenna is there. Its simulation has been done successfully, and the same its radiation characteristics are given over here. So, right click, far field report. In radiation pattern, if you go to the dB scale, so phi along 0, if we select. So phi equal to 0, I'm just going to select it at 27 gigahertz. Okay, only one half is generated, that is due to this default value. So here if you give minus 180 in the radiation, right, under radiation, if you give this settings, it is going to generate a complete pattern, right, from theta equal to minus 180 to plus 180. So the whole radiation pattern, if it is being cut, you will, how you will get, that is plotted over here. So add marker to the peak value. So with respect to the maximum value, which is 5.8, where is the 2.8 point? We'll look at it just a minute. So I've added a marker. So that marker, I'm just moving it around. So the place at which I'm going to get close to 2.75 or 2.8 dB, right, somewhere over here. So from minus 46 degrees to plus 46 degrees, we are going to have very good radiation pattern, meaning half of the power, peak power, right? Peak power, if it is in dB scale 5.69 or 5.7 or 5.8, close to that, then half dB, half the peak power is going to be 2.78 or 2.78 or close to 2.8. So the angle subtended by these two, basically minus 46 to plus 46, around 92 degrees of angle is being subtended by a single angle. Right? Now, this is with respect to the radiation pattern and all. Now, if you just copy this design and paste it again over here, right? You can, what you can do is you can copy the design and paste it over here. So newly pasted one, what we are going to do is see here a copy has been created. I'm just making it as an array, right? Array, and I'm just putting it as an array antenna, like this for our reference, right? Now what we are going to do is we are going to arrange this whole antenna as a pattern, right? All placed adjacent to each other. Like this, we are going to arrange. Now, how to do that is, see, we added a open region around the antenna for measuring the radiation pattern. Now, this open region, we will constrain it at the boundary of the dielectric itself. Right? So, see, this extra extension is there, right? That is called X padding. Along X direction, how much additionally we have added. Along minus X direction, how much we have added. Along plus Y direction, minus Y direction. Along vertical, right? Padding is given. In the bottom also padding is given for this box. Now what we are going to do is we are going to reduce that. So go and click at the create region. Now X padding, I want to make it as 0. 0. Y padding also as 0. And the Z padding, I've just put it like this. So if you click OK, you will be able to see that we have restricted that padding. That means all the side walls are right now arranged like this. Now go to the boundary and delete the existing boundary. Need to delete it. Then now we are going to perform this finite array domain decomposition method of antenna array. Finite array domain decomposition method, right? FADDM. Now what it means is we are going to repeat the whole structure again and again along one particular direction or both the directions to have a vast array of elements. How to do that is, for that we should have a master and a slave kind of boundaries along the x and y directions. So I'm going to select a face instead of select object. I'm using the select face and selecting this face and the respective opposite face. So what I have done is I have selected two opposite faces towards x-axis. So if you want to repeat the whole structure, then this is how you need to perform. So the air box is there, right? So that along the sides we are just placing like this, and right click, assign boundary, and coupled, and it is lattice pair, right? Right click, assign boundary, coupled, and lattice pair. Select that, it will ask what name would you like to keep it as. I'm just keeping it as lattice pair along the x direction. Lattice pair x. You click right, it is asking what are the scan angles to calculate the phase delay. So later on, if you are using scan angle type and scan angle theta, right? So initial value, what is it? It will ask, just click 0, 0, right? So this gives us, see, there is one arrow indicating from this side, that is pair surface. Now similarly, we need to select these two faces, this face and this face. Now why, I will show it in a 1 or 2 minutes. So first we are selecting these two faces, and then again right click, assign boundary, coupled, lattice pair. This time I'm going to name it as lattice pair Y. So click next and have it by default whatever value it is. So if you notice, the boundary conditions are like that. Lattice pair X is there, right? That means you're going to have a master and a slave. When you repeat it, along which direction you're going to repeat it, that you can specify it like this. And then a lattice pair Y is there. Then there is a top and a bottom surface which we didn't include as of now. So the top and bottom surfaces are going to, you need to right click at it. The bottom and top, right? It's exactly the bottom and the top. Right click, assign boundary, radiation. Only this one, it will be a radiation. Now we have assigned a lattice pair like this, and also like this, right? And we have the radiation pattern. Now once this is done, go to the model, create array. So name is A. I'll make it as a visible. Then how many antennas do you want along the lattice pair X? So there'll be an antenna. There'll be this lattice pair is there, right? So along this direction, along one direction, how many antennas do you want to place? You can place 8 antennas also, or 4 antennas. Let me just initially place 4 and 4 antennas. And I'm just clicking apply. See, it is generating 4x4 array. Right? If you generate 8x4 also, you can generate like this. 8x4 or 2x4. So initially, just for our preliminary analysis, you can take it as 4x2. Right? Adding cells, you can just add one. So active cells. So in certain cases, what will happen is you will be selecting, let's say, 16x16. Right? It will be like this. This is what a antenna. So around 10 centimeters, you can just imagine, right? Like around 8 to 10 centimeters wide and 8 to 10 centimeters along this direction. So within this itself, there are 256 antenna elements. Around 20 cross 20, 10 cross 10 centimeters. Within that, 256 antennas can be placed over here. Right? In certain cases, you might require like this. This is what a base station antenna will look like. But this requires extremely large computing facility. Probably even 128 GB RAM or 256 GB RAM would be a bit less. Right? You should really have a very high end. So instead, for regular i5 processor, you can go up to 4x2 array with a 16 GB RAM. 4x4 array can also be done. But also, if you're restricting the number of frequencies, then you can have the simulation done very quickly. Right, so I'll go ahead with a 4x2 array and I'll just show this. So right now we have a 4x2 array, and what are the active cells? So let's say if you don't want to excite any antenna, you want it to be there, but you don't want to excite it, you can make it as a passive. Otherwise, you can add it as a padding. Right. So instead, right now we'll make it as all active and click apply and close. So here we are having an array of 4x2, right? Four columns and 2 rows, 2x4 array. And now the thing is, you can right away start the simulation, but I would advise you first and foremost thing when you design a single antenna, please note these tips might not be given in any videos or anything. Based on the experience, I'm just telling what to do. Just make a note that the result that you have got, right? So once you get a very good result of S parameters, then, right, what are the points at which that you want to measure the radiation pattern? You take only those points in the array simulation. When you go for the array simulation, you don't need to put like 201 points. Instead, you can directly put it as 26 or 24 gigahertz to 28 gigahertz. Total points 5, meaning 24 gigahertz, 25 gigahertz, 26 gigahertz, 27 gigahertz, 28 gigahertz. So like this, be specific to which frequencies you want. You don't have to simulate completely. Only selective frequencies you put for the array simulations, right? Not for the individual antenna. Individual antenna, you have to analyze the complete band. Once you have analyzed the complete band, then come back over here and take the specific frequency points where you want to generate the radiation pattern. Now, this simulation might take slight amount of time, additional time. So I'll tell how to configure the sources. So once this is done, that's it, right? So you can start the simulation, right click, analyze, you can just give, right? It will start analyzing. Now, very important thing is the excitation. Go to the right, right click, edit sources. Over here, all the individual antennas are given over here, right? You can select 1 watt linear. If you are giving linear distribution, then you can give like this, or if any other pattern if you want to generate, that's up to you, right? So all 8 antennas I'm selecting like this. Now here you can put it as pi val times 1 plus theta val times 1. So what is this? I'll tell you in a minute. So this is a phase shift, progressive phase shift that we are going to give. So what I'm doing is I'm trying to give a pattern. So what you can see over here is this is row 1, column 1, row 1, column 2, right? So second row and third row and fourth row. There are 4 rows. So in each row, I'm taking 5 value as same. And next row, I'm doubling it. Next row, I'm doubling the phase. Again, I'm tripling the phase. And next row, I'm increasing the phase again. So progressively you are increasing the phase. Now with respect to the column, right, the power is, I mean, again the phase is doubled. So this is the phase shift that we are giving to individual antenna. So individual antenna, the phase shifts what you are giving are just given over here. So in this way, if you give and perform simulation, I have the result. I'll just show the result to you directly. Right. So what antenna which I designed, right? Its results I'll just show. So the S parameters. Okay, I think the results got deleted anyway. So see, this is the radiation pattern that I got for multiple antennas. If you are taking multiple antennas, right, I mean 4x2 antennas like this, and if you are going to plot the radiation pattern, then you will be able to get it as shown over here, right? So 18 times the input power. I mean, you are getting a gain. So gain in dB decibel, if you plot, you will be getting a dB scale close to 12, 12.8 or 13 dB. You will be able to get. Now, all you need to do is just scroll down, right? You select this array option after simulation. Go to the phi value, right? Over here, I'm just going to give it as minus 60 degrees. And I just clicked outside. If you notice, the beam has tilted towards the left. And further, if I'm just giving it as a minus 90 degrees, it is again tilting further to the left. So like this, you can form the beam. So again, now if I give the value as 0 degrees, long phi direction, it is exactly at the center. Now again further, if the beam, you need to rotate it towards the positive side. So you have it as like plus 30 degrees. To the other side, the beam is rotating. Now you increase it to 60 degrees. Now again, it is rotating towards the right. Right, the main beam is rotating towards the right. So like this, you can rotate the beam without rotating the structure. Structure is same. Just by changing the phase shift, you are rotating the main beam. Right. So in this way, you will be able to effectively generate the pattern. Right. So just a minute. Anyway, this. Right. So this is with respect to one direction. That means the beam previously it was when you have 0, you are getting this beam, right? Now this beam, if you notice, let me go to the linear scale just to show its significance, right? And this is the linear scale, right? Now again, if you want the beam, previously you had kept like this, right? So the beam was rotating in one direction. If you want to rotate in another direction, we had given a theta val in the excitation, right? So there, if you give the phase shift as 30, it will generate a rotating beam. The beam is actually shifted to the other side. If you increase it to 60, again, the beam is shifting upward. You can see it is not at the 0, but it is shifted towards one direction. If you give it as minus 60, the beam will be bent towards towards this direction. So basically, you arrange multiple antennas and you give the phase shift between the rows and the columns. You will be able to just rotate the beam, right? So if theta value is 0, again, when you place multiple antennas like 16 cross 16 antennas or 8 cross 8 antennas, you will be effectively able to generate a very good radiation pattern. Even this is not very focused. We can generate much focused like a pencil beam if multiple antennas are included. Now, there are advantages and disadvantages which I would like to tell with respect to this approach. Right? If you have very good hard disk space and RAM is limited, I repeat, if you have very good hard disk space and RAM is limited, then if you simulate without this uh, this approach, see what approach I did was basically finite array domain decomposition method, wherein we are just taking one antenna and replicating it using the boundary conditions. So without boundary conditions, if you are actually copying and pasting all the elements again and again after some spacing, in that case, RAM can be less, hard disk space needs to be extremely high because the simulation result, uh, um, probably if you have some close to 50 antennas, if you have, when you're simulating the result, it is going to be generating 128 or 140 GB space. It is going to occupy if you are not using this approach. But with less RAM, more hard disk space, you can perform. Unlike this domain decomposition method, instead, if you are drawing one antenna, right, what I am telling is, I'll just show it. Right, we have a single antenna over here. I'll copy and paste it over here. Right click paste. Right. So instead of having the boundary conditions defined like that, what if you select all these structures, the radiating, the feed, these ones, if you are going to replicate, right? Edit, duplicate along line. So here, let's say 0, 0, 0, and along x direction, I'm going to replicate, let's say, at 5.55 mm and 0 and 0. Right? So 5.5 mm, sorry, 5.55 mm, 0, 0. So like this, if you are increasing the numbers, right, the antenna elements, physically you are drawing everything. So in that case, it would take too much of hard disk space. RAM space can be somewhat manageable. RAM, it will work with a relatively lower RAM. But the domain decomposition method, what it does is it requires too much of RAM. Hard disk space, the simulation, total simulation file of 50 antennas, probably it will generate file size or a folder size of close to 2 GB. But simulation RAM should be extremely high for 50 antennas. Right, so this is the trade-off that you need to require. So domain decomposition is this method, and the conventional method wherein we are going to just replicate the number of antennas. So here you see, you can see multiple dielectric materials, multiple feed lines, multiple patch antennas. Individual patch are separately placed like this, right? So if you are going to do something like this, it is going to be taking too much of um, hard disk space, but the simulation, total simulation, same result you will be getting. But hard disk space, it will be taking too much, but RAM is less. With less RAM, you can do the conventional approach. So that's it from my side. This is with respect to the antenna, individual antenna simulation and an array antenna simulation as well. Right, I'll stop right here. So array simulation, those are interested to do some research work with respect to antennas and array simulations for either this 5G. See, even your mobile phones have at least, the true 5G mobile phones will have at least 4 antennas together, right? Like this, 4 along one direction and 4 along another direction, it will be there. A minimum of those many antennas will be there, right? So anywhere the next generation of communication, be it the wireless autonomous vehicles, or multiple radars are going to be included over there in the autonomous vehicles, and there also you require multiple antennas and array simulations and all are necessary. So if any of you are interested, you can just contact me. So I'll be able to help you out in giving some research topics related to these as well. And regarding industry consultation also, I'm working with some industry for close to 50 antennas, and based on that experience only, I was just giving you suggestions that if you follow one approach, it would save you, I mean, RAM, even if lower RAM is there, you will be able to, I mean, your system will be able to generate the result, but it would provide, I mean, it would require extremely large RAMs, I mean, hard disk space. It will offer. So each and every iteration, if you want, so once you need to simulate beamforming, you just need to change the phase of phi val and theta val. After simulation, if you change, your beam is going to be generated. That is the one advantage of the beamforming approach, the domain decomposition or whatever array it is. So Ansys, you don't need to repetitively simulate again and again for different beams, right? So that is one advantage. But yeah, that's it from my end. Again, so if any of you are interested for any research topics, please let us know. So I'll stop right here, and I'll also stop the recording. Yeah, ma'am, I'll stop the recording, ma'am.
Okay, sir. Okay, sir.
Okay.